In this video, I'll discuss Tf-Idf, a popular measure of word importance in NLP and information retrieval tasks. I'll talk about the intuition behind Tf-Idf, followed by the equation for computing it. Then I'll work through a case example to show how it works in action. In the last video, we talked about basic word representations and specifically focused on the bag of words model. However, just defining a word by the binary presence or raw frequency of the words around it may produce less than desirable results. Because of that, you may find yourself wondering, what are some other ways we can build vector representations for words? One approach we can take is called Tf-Idf, which is short for term frequency times inverse document frequency. When we build Tf-Idf vectors, we define the meaning of the word based on the counts of words in the same document, as well as overall in our corpus, which has the effect of placing higher importance on words that are more unique to specific documents. We compute Tf-Idf using co-occurrence matrices. Tf-Idf originated as a tool for information retrieval and is still used for some tasks in that domain as well. When we build our co-occurrence matrices, we generally represent the rows as the words in our vocabulary and the columns as documents in our training set. These documents might be things like entire books, or they might be individual training set instances. Later on, if we want to use Tf-Idf scores instead of raw frequencies in a bag of words representation, we would go ahead and compute the Tf-Idf score for each word in our vocabulary, given our specific training set instance. You can see a term document co-occurrence matrix here, where we're working with this toy case where we have 4 words and 4 documents. We can see from the matrix, for example, that the word wit appears 3 times in Henry V. The row corresponding to wit could be considered a word vector, with each dimension corresponding to a document. So in this case, words that occur in similar documents would also have similar vectors. Just looking at the column distributions here, we can see that we appear to have 2 groups of similar documents. Julius Caesar and Henry V appear to be relatively similar to one another, and As You Like It and Twelfth Night also appear to be pretty close to one another. We can then go ahead and plot these vector points to see where they exist in our vector space. In this case, our vector space is 4-dimensional, but it's hard to represent a 4D space on a 2D slide. So I just plotted the Julius Caesar and Henry V dimensions here. We can see that the words fool and wit appear to be pretty close to one another in our vector space, whereas battle and good are a bit further away. Now, with Tf-Idf, we represent context in terms of documents, but in other types of word representations, it's more common to represent context in terms of neighboring words within a predefined context window. We still use co-occurrence matrices for this, and these matrices might be referred to as term-to-term matrices, word-to-word matrices, or term-to-context matrices. In these matrices, the columns also correspond to words. So the dimensionality of a word-to-word matrix would be the vocabulary size by the vocabulary size, with each cell being filled by the number of times that a given context word appears in the same context as a given target word in a training corpus. Common context windows include the entire document, like what we use with Tf-Idf, or predetermined spans surrounding the target word. The size of that predetermined span is a bit dependent on the size of your corpus, and also the anticipated importance of long-range context for your specific task. Here's an example context window of size 4 from the textbook. So as you can see, all of the words pointed to by the arrows would be considered as being in the context of the word strawberry. If we then needed to create a word-to-word co-occurrence matrix, we would use this context window to guide our creation of it. So anything outside of the context window wouldn't be considered as part of the context for the target word, whereas anything within it would be counted. So in the example we just saw, and also with our earlier discussion of bag of words models, our vector representations have ended up being comprised of just raw frequency counts corresponding to word presence or word co-occurrence. However, that really isn't the best way to measure the association between words, because some words naturally occur in language way more frequently than others. If we just use raw frequency, we'd end up with high co-occurrence counts for words like the, regardless of which words they were paired with, and this would just end up adding noise to our word representations. What we really want instead is to know about words that co-occur frequently with one another, but less frequently across all texts in our training corpus. So this is where Tf-Idf comes in handy, because it's designed to handle exactly that problem. Tf-Idf is super easy to compute. It's just a combination of term frequency, defined as the frequency of a word T in a document D, and document frequency, defined as the number of documents in which the word T occurs. An important thing to be aware of is that document frequency is different from collection frequency, or the number of times the word occurs in the corpus overall. If a word occurs 5 times in one document and 1 time in another document in the corpus and nowhere else, the document frequency would be 2. So the IDF in Tf-Idf stands for inverse document frequency. This is exactly what it sounds like. Basically, we take n, where n is the total number of documents in our training corpus, and divide it by the document frequency for a term T. So the IDF ends up being higher when the term occurs in fewer documents, and lower when the term occurs in a lot of documents. Sometimes people will compute both TF and IDF in log space. If you do that, just make sure to do smoothing for term frequency so you don't end up trying to take the log of 0. And now that we have TF and IDF, we can compute Tf-Idf by just multiplying them together, and there we have it. To see what it's like to compute Tf-Idf in practice, we can work through an example. So let's say that we have the same 4 words that we were using previously, and then we just have some generic documents, D1, D2, D3, and D4. We want to find the Tf-Idf value corresponding to the first cell in our matrix. So it's the Tf-Idf for battle, given that we're working with document 1. We start out by finding the term frequency for this case, so we're looking for the number of times that battle occurs in document 1. We can clearly see from our table that it occurs 1 time in document 1, so we'll go ahead and make a note of that. Now we need to find the inverse document frequency for battle. So here's where we need to take a peek at our larger corpus. This is based on an example from the textbook. So the textbook tells us that battle occurs in 21 of Shakespeare's plays, and that this corpus of his plays includes 37 documents overall. That means our inverse document frequency for battle is going to be 37 divided by 21, or 1.76. Now we just need to put everything together. So we take our term frequency 1 and multiply it by our inverse document frequency, 1.76. This gives us a Tf-Idf of 1.76. If we were doing this in log space, we would take the log of 1 plus an extra 1 for smoothing purposes, and multiply that by the log of 1.76. That would give us a score of 0.074. So we can go ahead and replace our raw frequency count with a Tf-Idf value instead in our table. If we want to convert our entire matrix here to a Tf-Idf matrix, we would just go ahead and perform similar computations for every other cell also. Once we do that, we can look at how our original term frequency matrix compares with our new Tf-Idf matrix, and we see some interesting changes along the lines we expected. We see that since the word good occurs in every single document, it has an extremely low Tf-Idf score. That's because since it's so common across the corpus, knowing whether it's present in a given document isn't going to be very informative when trying to, for example, make classification decisions. On the other hand, the word battle didn't occur much in general, but it did occur noticeably more in some documents than others. Our Tf-Idf scores reflect the increased importance of this word for making downstream classification decisions. Another thing to note with our Tf-Idf vector is that it produced pretty sparse representations. This would be even more obvious if we looked at the entire corpus, or even a larger subset of it, instead of just a subset of 4 documents. This can be problematic because it's often fairly challenging for machine learning models to learn effectively from sparse feature vectors. Despite this, Tf-Idf still remains a useful starting point for vector space models, and is often combined with classic machine learning models like logistic regression and naive Bayes.